Welcome back. So I have been in the studio all day today. It is getting late, but I have stuck with it here because I am super excited about this next lecture. We're going to start solving these generic systems of equations, x dot equals ax, using eigenvalues and eigenvectors. So I'll just put that up, solving x dot equals ax with eigenvalues and eigenvectors. And I'd say this is one of the culminations of all of kind of introductory applied math, linear algebra, and differential equations is going to be covered in this and the next two lectures, where we really break down how to solve matrix systems of differential equations using eigenvalues and eigenvectors. Specifically, I am actually going to derive the eigenvalue and eigenvector equation as a necessary coordinate transformation to simplify this differential equation. So this lecture is going to end on kind of deriving from scratch the equation from which we obtain eigenvalues and eigenvectors, specifically to solve this, this system. Okay, so I'm going to write out the objective, I'm going to solve a simple case, and then we're going to jump into eigenvalues and eigenvectors. So we basically want to solve, a generic system of equations, a general system of ordinary differential equations, x dot equals ax, system of equations, and specifically, x is a vector of states now. There are multiple, x1, x2, x3, x4, multiple components of this vector x. A is a matrix, and this is a system of coupled first-order linear ordinary differential equations. First order because we only have one derivative in time, coupled because presumably these derivatives depend on all of the other states in this vector x. And linear because this derivative x dot is a linear combination of the states in x. That's literally what a matrix times a vector means. That's a linear combination. Okay? And so what I'm going to do is I'm going to start off with the simplest possible case where this A matrix is diagonal, meaning that the dynamics are decoupled. Okay? So kind of case one is where what we call decoupled dynamics. Decoupled dynamics, I'll tell you what that means. So remember when we had kind of our first example of a differential equation, x dot equals lambda x. The example we introduced was the population of bunnies, and bunny populations grow exponentially. What I mean by decoupled dynamics is going to be, let's say that the state x refers to the populations of different animals, but they are kind of in a zoo. So they're each cordoned off into different zones, and so that they don't interact. That's what I mean by decoupled. So we're going to have the populations of like bunnies and wolves and antelope. And so I'm going to have a state vector with multiple populations, and they're each going to behave linearly, but they're only going to depend on themselves. They're not going to be coupled yet. So I like to call this kind of, my example I think about is different animals in a zoo. And it's a zoo that's big enough where they can grow exponentially. It's kind of like Hilbert's Zoo or something like that. Okay, so the populations are separate. That's the key thing, is that the populations are separate. And so I'm going to write down this differential equation. So we have, let's say our state vector x has a bunch of components x1, x2, all the way to xn. Let's say I have n animals in n different zones in this zoo. And I'm taking ddt of this state vector. This is just x dot, where x is a big vector containing all of these components. And we're going to say that this equals, in the case of decoupled dynamics, this is, again, a matrix A times x1, x2, xn. But now what we're going to have is that this is going to be a diagonal matrix. So x1 dot is only going to be a function of x1. We're going to call that, let's say, lambda 1, 0, dot, 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 0. The second animal, let's say x1 our bunny population. Okay, x2, let's call that our wolves. x2 dot is only going to be a function of x2 because they live in their own, room in this big zoo. So they actually are not interacting with the bunnies, so they have no influence. x1 has no influence on x2. x2 dot is only equal to a number times x2. We're going to call that number lambda 2. So x2 dot equals lambda 2 x2, and that's the only, these are decoupled, so the wolves are alone, the bunnies are alone, dot, dot, dot. It's very lonely. Actually, I think they're fine with all the bunnies together. And then kind of every term is like this. And now the xn dynamics, the nth population, whatever, only depends on the xn population with this lambda n proportionality. So this is really, really simple. In some case, I didn't even need to write this as a system of differential equations in a matrix form. I could have literally just written this as, so before I forget, I'm going to call this matrix D because it's diagonal and decoupled. Okay, so this is a special case of an A matrix where it's diagonal and decoupled. I didn't even have to write it like this. I could have literally just written down, x1 dot equals lambda 1 x1, x2 dot equals lambda 2 x2, dot, 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 xn dot equals lambda n x. And of course, we already know the solution of this. We can just solve them each independently. We could say that x1 at time t is e to the lambda 1 t times x1, my initial condition, x1 naught. And x2 at time t is equal to e to the lambda 2 t times that initial wolf population, x2 naught. All the way down to xn at time t equals e to the lambda n t times xn naught, the initial population of that nth animal population. And so these are really easy. Because my dynamics are decoupled, it's almost trivial for me to solve the system of equations. And if I like, I can write this solution again in matrix form. I can just say, this is x1, x2, dot, 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 xn, this big vector x at time t is equal to, and now I have a diagonal matrix of exponentials. I have e to the lambda 1 t, 0, dot, 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 0. I have 0 e to the lambda 2 t, dot, 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 0. So this should be pretty intuitive at this point. 0, 0, e to the lambda n t times my initial conditions, times x1, x2, dot, 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 xn, this vector evaluated at time 0. Okay, and so this is really, really simple. This, if this matrix here was D, a diagonal matrix, then this matrix here is e to the diagonal matrix t. Okay, it's literally a diagonal matrix where I exponentiate all of the diagonal elements times t. This is e to the dt. I haven't defined what a matrix exponential is yet. I'll define that in a couple of lectures. It's really easy. You literally take the Taylor series for e to the x, and you just plug in a matrix for x, and you work it out. That's how you take matrix exponentials. And this is what you get for decoupled dynamics. Okay, so this is really, really, really easy to solve my system of equations x dot equals ax if A is a diagonal matrix D. Good. So I hope I've convinced you that that's really, really easy. Okay, this is the full solution. But most of the systems we deal with in the real world are not going to be nice and diagonal like this. You know, you're not going to be dealing with animals in a zoo. You're going to be dealing with the populations of bunnies and wolves and antelope in the wild, and they're not going to be separated. They're going to be interacting with each other. So there's going to be cross terms in this matrix, and in general, A is not going to be diagonal. It's going to be a full gnarly matrix, and it's not going to be easy to solve it like this. Okay, and so that's where eigenvalues and eigenvectors are going to come in. What we're going to try to do is we are going to try to find a coordinate transformation that turns this system into a diagonal decoupled system. I'm going to erase this and then write that out. 1 second. Okay, so we now know that it's easy to solve these matrix systems of equations if the matrix A, relating all of my derivatives to all of my states, is diagonal and decoupled. So now the objective here is going to be for this generic system, for a general system, x dot equals ax. What we're going to try to do, we want a change of coordinates. We want a new coordinate system or a change of coordinates. And I'm going to write this as x equals t times z. So t is going to be a matrix, an invertible matrix, a matrix that has non-zero determinants, so you can compute its inverse. So I can go from x to z or z to x by multiplying by the matrix t or its inverse. So I want a change of coordinates into a new coordinate system z that diagonalizes my ordinary differential equation. That diagonalizes my ODE. Specifically, what I want in this z coordinate system, I want z dot to equal a diagonal decoupled matrix times z. Okay, that's my entire objective now. If I have a generic system, if someone hands me a system and they say, hey, Steve, can you model this system? I'm going to first try to find a coordinate transformation t that goes back and forth from x coordinates into a z coordinate system, where in this coordinate system my dynamics are decoupled and diagonal. Because here I could easily solve this. We know how to solve this. Z as a function of time is e to the matrix d times time times my initial conditions. I know how to solve this. This is easy to solve. We just did it. So now I'm going to try to find this coordinate transformation that diagonalizes my system. Okay? And specifically, we're going to do this, and we're going to derive the eigenvalue and eigenvector equation. So I'm going to take the time derivative of both sides of this thing. Maybe I'll go orange here for a minute. So I'm going to take the time derivative of both sides, and I'm going to take t z dot, that equals x dot, and x dot equals ax, so that equals ax. And so that implies that tz dot equals ax, and specifically x equals tz. So here I can plug in, I'm trying to get an equation for z, so I can basically say that tz dot equals a times x, and that's a times t times z. This equals a times t times z. And now I'll remember to put all of these matrices and vectors. So big capital letters, generally I use to mean matrices. So a and t are matrices. Z and x are vectors. Okay, that's the state of my system x, and z is the state of my system in some different coordinate system. Okay, and I'll tell you what I mean by a different coordinate system in a minute. Okay, so now this is starting to get somewhere. Now we have a differential equation only in z, but I have this pesky t out here, so I'm going to try to invert this t and multiply on both sides by that. So that gives me z dot equals t inverse a t times z. And remember, I'm specifically trying to find this matrix T. That's what I mean by a coordinate transformation. It's just a matrix T. Linear coordinate transformations are matrix multiplication. That's what linear algebra tells us. And so specifically, I'm trying to find a T matrix so that this quantity here is a diagonal matrix. So that z dot equals this stuff here is diagonal times z. And so specifically, like we can write this pretty simply. We want a T matrix so that T inverse AT equals this diagonal matrix. Okay, that's what we want. Okay, writing all of these double underbars is getting a little tedious, but I'm going to stick with it because I think it's important. So we want a T so that this is true. We had this system. We want to find a coordinate transformation that diagonalizes our dynamics. And if we had a T so that T inverse AT equals a diagonal matrix, we've done it. Okay, and so the last step, this is actually like very, very simple. The last step here is I'm just going to multiply both sides again by T inverse, on the left by T to kill this T inverse. And so that is going to give me AT equals TD. I multiplied the left by T on both sides, so I get AT equals TD. These are matrices. This is the eigenvalue and eigenvector equation. This is the eigenvalue equation. Eigenvalue equation. I'm going to put some big exclamation marks because this is a huge deal. Literally, the diagonal elements of D, the diagonal elements of D are the eigenvalues of A, and the columns of T are the eigenvectors of A. Okay, D is a matrix, A is a matrix. So I haven't shown you how to solve for T and D. That's a whole nother lecture. I'm going to do that next. We're going to show how for a specific A matrix we can find these eigenvalues in D and the eigenvectors in T. But this is the equation that I'm solving for T so that my dynamics become diagonal. Those T are the eigenvectors of A. That's exactly what this means. This is the eigenvalue eigenvector equation. So for me, I always found it very counterintuitive that you take a linear algebra class and they write down all this abstract kind of algebra, and they write down here's what an eigenvalue and eigenvector is without motivating it. For me, this is why we care about eigenvalues and eigenvectors in the first place. This is why I care about eigenvalues and eigenvectors, because eigenvectors of a matrix are a change of coordinates so that it becomes diagonal. These eigenvectors provide a change of coordinates. In these eigenvector coordinates, my dynamics are diagonal. That's huge. That means I can solve any linear system of equations. Okay, so I'm almost done. I think what I'm going to do now is I'm literally going to draw a picture of this for you. So I'm going to say, I'm going to draw a picture of this eigenvalue equation, and then I'm going to, end this lecture. And in the next lecture, we're going to figure out how do you compute these things, and then how do you use these T's and D's specifically to solve this equation, and then to go back and write it in terms of my original x coordinates, which is where I probably measured things and where I actually care about things. Okay, so I have my A matrix here. I'm just going to draw it as a big square matrix. It's an n by n matrix. Okay, that's A. This T matrix has columns, T1, T2, dot, 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 all the way up to Tn. These are column vectors, where each column vector is an eigenvector of A. And this is equaling Now I maybe drew this just a tiny, tiny, tiny bit too tall. That's going to be a problem. Okay, these are the eigenvectors of A. Let's give myself a little more room here. So A times T equals T times D. So this is going to equal, again, T1, T2, dot, 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 all the way up to Tn. This is, again, my T matrix, times D, my diagonal matrix, okay? And my diagonal matrix, again, just had these lambdas, these eigenvalues. Sometimes in my notes I call them D1, D2, D3. Here I'm just going to call them lambda 1, lambda 2, lambda 1, lambda 2, dot, 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 lambda n, zeros everywhere else. And here's what I want to point out, is that if I take this, a column of this, so if I want to multiply this matrix by this matrix, what I do is I take the first column of D and I kind of knock it over on its side and multiply it by every row of T. That's my first column. Then I take the second column of D, I knock it over on its side and I multiply it by all of the rows of T. That's my second column, and so on and so forth. But if you take, let's say this lambda 2, this column here, and I knock it over on its side and multiply it, because it's zeros everywhere else, it's only going to multiply the T2 eigenvector. So this is a very useful property of this diagonal matrix. This literally is going to equal lambda 1 T1, that vector, lambda 2 T2, that vector, dot, 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 lambda n Tn, that vector. Okay, and so what we're basically going to find is that A times T1 is going to equal lambda 1 T1. A times T2, the second column of this product, is going to equal lambda 2 T2, and so on and so forth. I'm going to get a bunch of equations that look like A times T equals lambda times T. Okay, like for the kth eigenvector and the kth eigenvalue, this is going to be true. Okay, so you can write it in this matrix system of equations, or you can write it for a specific eigenvector T or eigenvalue lambda. Now here Tk is just a single eigenvector corresponding to that particular eigenvalue. These come in pairs, is what I'm trying to say. Okay, let's take a big step back. We want to solve these systems. Generically, they are not going to be diagonal. We know that we like diagonal systems because they're easy to solve, but generically they're not going to be diagonal. So we try to find a coordinate transformation T, a matrix T, that can map me into a new coordinate system. Like literally, Z is going to equal T inverse of X. So I can go from X to this new coordinate system Z, so that Z has diagonal decoupled dynamics. So it's easy to solve my dynamics in Z. Now if I go through some algebra, we find that this is the condition. So if Z dot, these are the dynamics in my Z coordinates. And so if I want these to be diagonal, then this has to be true. And I can rewrite that in terms of my eigenvalue equation. So this is the equation I solve to get that eigenvector coordinate transformation T that diagonalizes my matrix A. And given that, we're going to be able to solve generic systems that are really nasty in terms of easy linear algebra. Okay, and that's all coming up next. In the next lecture, I'm going to show you how do you actually compute eigenvalues and eigenvectors. And in the lecture after that, I'm going to show you how do you use that to actually solve these differential equations that we want. All right, thank you.